Says that very loudly. All right, we'll get started in 30 seconds or so. I hope everybody had a good weekend. Hope you got a chance to get outside on Friday because it was gorgeous. And I don't know, it's hard to believe we're going to have a day that nice until like March or April. So I hope you got a chance to get outside. I was telling you at the beginning of the semester that I've been sort of interested in archery. So there's a couple places that I've been shooting, and one of them is in with the archery club here at RIT. So they meet on Fridays. So I was outside in the sunshine shooting my bow and arrow outside. So that was pretty fun. I hope you got a chance to do something fun. I know it's kind of midterm season, right? These couple of weeks. So I hope that that's winding down for you as well. And then when that's done, we can start thinking about final exams. Right now, the final exams for this class are going to be. See how it was a nice segue, I think. Right. See, the final exams for this class. If the first third is closed systems mostly, and the second third is open systems mostly, then the final third is going to mostly be cycle analysis, right? So we did do sort of this 4-component rank and cycle problem on the second midterm. And then we'll just be going, through a series of different cycles. Now, my objective is to sort of teach you that all of these cycle analysis problems are kind of the same. We'll just make different choices about, how do we characterize the cycle? What's the energy benefit? What's the energy cost? Um, what's the fluid will be different. So maybe we're going to fix the states differently, right? And then if it's open or closed, we'll use different equations for, say, the first law, right? But I want you to kind of start to try to think about it. It's always the same problem. It's always the same starting point. And then you're just, you're flipping to different pages in sort of like a choose your own adventure book. If you want to follow along today, the starter sheet for today is under Scherzer's videos and starter sheets in content. And it's this one in between lecture 28 and 29, this bonus lecture for the Rankine starter sheet, Rankine Regeneration. So if you click on that, you'll get something like this. And this is because basically when I put the syllabus together, I only had 2 lectures in week 7, I think it was, or something, right? And I'm using that extra lecture now so that we have a chance to go through these Rankine regeneration problems, or at least one of them. And I'm doing that because I think that, every cycle that we talk about has its own little wrinkles, right? Its own thing that makes it difficult. But I think that this one is one of the 2 most difficult ones that we do because the mass splits, right? We talked about how the mass splits so that the mass flow rate is not the same everywhere in the system. And I think that makes it a little bit tricky. Before we get started doing this problem, though, I just did want to make the announcement that I have posted grades for the multiple choice problems in the exam, and then also for the last problem in the exam. So you should be able to see sort of your result and comments in the long answer problem. So we will give time at least till next Monday if you think that we made a mistake grading. I don't know exactly when the grades for the second problem will be up, but certainly before Wednesday, and possibly even before that. If people do have questions about the exam that they'd like to voice now, I'll give you a second to do that if you'd like to ask questions. Okay. So if, let's say this is an exam, right? And I open this up and I see a Rankine regeneration cycle. Oh, looks like there we do maybe have a question here. Is there an SIS grade and a My Courses grade? Which one is the actual grade you received? So My Courses will give you a current numerical grade, what you have in the course. I think by SIS grade, maybe you mean letter grade. I don't know what the conversion from the numerical grade to the letter grade will be exactly, because it does change a little bit every year, right? Because of the way that we do things in this class. We try to give ourselves the freedom to challenge you on exams, which means that we don't hold tight to, you need to get over a 90 to get an A. So typically the grading scale looks a little different in this class. Once we have all the grades from the second midterm, I'll post another relative standing sort of graph so that you can see kind of where you are if the class ended today. But remember, the final can still overwrite one of your two midterms if you do better on the final than the midterms. Looked like there was another question here. Okay. Yes. Yeah. So I will put up another breakdown. We just have to have all the grades in first. Okay. So if this was a final and I see something that looks like a Rankine regeneration problem, what I want to do, I like to do this in color, but you could do this any way you want, is I like to just right at the beginning, before I even start to do anything else, is kind of show where the mass splits, right? So I'll try to keep the same color coding that I used in the lecture, right? So here we have, this is Y times M dot, right? Remember, Y is some percentage of the mass flow. It's probably fairly low, like maybe 25% or less, right? The majority of the mass flow keeps going through the second turbine, right? But some of it comes off here, right? So then there's this bit that goes through the second turbine, through the condenser, through the first pump, and into this open feed water heater, right? So everything on this line is going to get, oops. So, if all the mass flow rate went into here and I took out Y percent of the mass flow rate and we're at steady state, then this must be 1 minus Y times the mass flow rate. So again, if Y was 20%, right, then 20% goes here, right, and 80% goes along this blue line. Right now, then in the open feed water heater, everything comes back together, right? So now coming out of here is going to be the total mass flow rate, right, through the pump, through the steam generator, and through the first turbine until we get to this node where things split up. So this is going to be the total mass flow rate. Now, it doesn't take too long to do that. And I think doing that gives me a reference. So I can keep looking back up there to see, oh, what's going on when I do a first law analysis on a particular component. I can look at my picture to see what mass flow rate is involved where, right? And I like that because it means that I'm like thinking on the fly less, right? I'm trying to standardize the process, right? So I like to do that. I know some people use colors on the second midterm, and I always like to see that. Just for me, it helps. But if you've got a different method, that's fine. I took this problem right out of the textbook, right? So these, it's a little bit here. I'm just going to zoom out for a second, right? When we look at this problem, it's maybe a little bit daunting, right? There's 7 different states, right? There's 2 turbines and 2 pumps, and all 4 of those components have isentropic efficiencies, right? So that's really like 11 states that we have to fix. And when we look at the state table here, there's not a lot of information. And actually, the state table, this information wasn't given on a state table. It was all given sort of in text, right? So I sort of, read the text and went through line by line and put information in here. Now, if this was an exam, you would have more information than this on the state table, right? I would, populate some of it so that, you could still go through and do parts of the problem, but you wouldn't have to fix all the states, right? We all know that fixing states takes a certain amount of time, and I'm not going to have you fix 11 states because you probably, that itself maybe takes more than half an hour. And I don't want to be testing you on the final exam on like, can you do linear interpolation? Right. So some of these might be blank, but you would expect on a final to see more of a state table filled in than this, particularly if it has this many states. But that doesn't mean we'll still go through. I won't get numerical answers, but I'll show you how to fix all these states. Because just because you'll see some of a state table filled in a final doesn't mean that, you don't know which part's not going to be filled in, right? So it's still good to talk about how to do the whole thing, right? The first thing that I would look at, though, in a state table, right, and we'll go through the states at the end because I'm a big advocate of, doing the symbolic solutions first, right? But here, right, I can see in state 1, I have two independent intensive properties, assuming that's superheated vapor, so I can fix that one. I can fix state 4 right away because it gives me a pressure and it tells me that it's saturated liquid. And I could fix state 6 right away because, again, it gives me a pressure and a saturated liquid. So even though I look at that and I see I could do that, my advice is always going to be get the symbolic solutions first, so you don't spend your time. Maybe you spend a bunch of time interpolating to find like specific volume, and then you find out that you don't need it because it's not in any of the equations that you have, right? So instead of doing the numerical stuff first, it also tells us isentropic efficiencies of all the turbines and pumps. So instead of doing the numerical stuff, I'm just going to go straight to the different parts of the problem, and I'm going to try to get symbolic solutions. Or in the first case, I'm going to draw what my TS diagram looks like. Because again, that part is going to be the same all the time, right? Because that's the process, right? And this is kind of what engineering is about, right? Is that if you set up good processes, you'll get good answers more often than not. Even if this was some kind of crazy cycle, like if you can look through the textbook and you can see some pretty exotic diagrams here, maybe with 4 turbines, an open feed water heater between the first 2 turbines, reheat between the 3rd and the 4th turbine, and then a closed feed water heater between the 3rd and the 4th turbine. And that's scary if you just look at it, right? If you saw something like that on an exam, the first thing that I would think if I was an undergraduate was like, oh my God, how do I do any of this, right? But then the next thing I hope that I would think is trust the process, right? Do the first law on the different components, get your big, equations, ask yourself, what's the benefit? What's the cost of the cycle? What's the working fluid, right? That's going to help you. And then, are each of these components open systems or closed systems, right? But the first thing we want to do here is draw a TS diagram. Now, the only cycle we know so far is the Rankine cycle, which deals with water as a working fluid, and we're boiling it. So anytime we're boiling something like water, that means we need a vapor dome. Some of the cycles we look at starting next class, we'll have ideal gases as the working fluids. And if it's an ideal gas problem, you don't draw a vapor dome on the TS diagram. Now, what I like to do with these TS diagrams is first figure out how many pressures there are in the problem, right? So I'm going to draw constant pressure diagrams. So the highest pressure is the pressure that comes out of this second pump, right? So this is, I'm going to call it PH for high. This is going to be associated with state 7 and then state 1. Right? Because what happens is after state 1, I go through that first turbine and the pressure goes down. Right? And then I would go through the second turbine and the pressure goes down again. Turbines drop pressure and pumps increase pressure. So now I have my lowest pressure. This is going to be after the second turbine, right? So this is going to be, I'll call this P lowercase or L, right? So this is going to be the states that are associated with this are state 3, state 4, and then after state 4, we go through the pump, the first pump, right? And then what the first pump does is the first pump's job is to get the pressure of this saturated liquid equal to the same pressure as the fluid that comes out of that first turbine. Because when we mix these two things together, we want everything to be at the same pressure. Because if this pressure was lower than this pressure of fluid coming in, we might get backflow going this way, and we don't want that, right? So we want all these things at the same pressure when we mix them. So we have some intermediate pressure here, which I'm going to call PI for intermediate. Now, the states that are associated with that intermediate pressure, state 2, which comes out of the first turbine, so that's in between my 2 turbines. And then in between my 2 pumps, I have state 5 and state 6. So that's the first thing that I want to do is I want to identify where my pressures are and draw my constant pressure lines. The second thing that I'm going to do is I'm just going to march kind of, component by component, right? So I'm going to assume that state 1, we're going in here at a superheated vapor, right? They gave us a temperature and a pressure. So now, I just am drawing this, so I don't actually know if state 2S which is vertically beneath state 1. I don't know if that's going to be under the vapor dome or outside the vapor dome, right? So I don't trust too much in my sketch here that says that this is a superheated vapor, but that's where it looks like it is. And then state 2 is going to be on the same pressure line, but it's over to the right. Right? So this was the ideal first turbine and the real first turbine. Then I have an ideal second turbine as I go from state 2 to state 3S. Again, my sketch kind of shows that this is under the vapor dome, but who knows, right? Because it's just a sketch. And then my real turbine over here is state 3. All right, so now I've gone from 1 to 2 to 3. Now, what I do as I go from state 3 to state 4, the numbers on this diagram are not correct. I just pulled this picture off the textbook, right? But as I come out of the condenser at state 4, it tells me I'm still at this low pressure, right? So state 3 and 4 are at this low pressure, but I'm a saturated liquid. So now I've got state 4 over here, and my process from state 3 to state 4 looks like that. Then after state 4, I go through this pump. So I have the ideal version of this pump, right, which would take me up to state 5S. And I have the real version of this pump, which goes up and to the right, here to state 5. I've kind of crowded this in a little bit. But what happens as we go from state 5 to state 6, in this problem, they told us enough about state 6. It said that it was a saturated liquid at this intermediate pressure, right? So state 6 is over here. I have enough information to fix state 6. Notice that we've also gone from state 2 to state 6, right? So what happened here is as we went from state 5 to state 6, we added some heat into the fluid, right? But that heat came from this enthalpy that was locked up in state 2. Right. So this, we talked about this before. This is like, you know, if you sign up for like a 5K or something and they give you a t-shirt, it's not that the t-shirt is free, it's that it's included in the cost, right? So this is the same thing where we've already paid for this heat, right? We already burned the coal. That's what the regeneration system does, is it's using some of the heat that we already have to preheat this fluid. So now we go from state 6 to state 7S, and then the real pump is going to take us to some point at the same pressure that's to the right of that, state 7. And now we go up over here. And this is my cycle. So that's how I do it. I try to find the constant pressure lines. And then I try to start at the turbine and go state by state. So we do have a question here. Yeah, it's a little tricky. So the question is, we do sort of go from state 5 to state 6, but also from state 2 to state 6. So, I mean, you could draw a line here as well. I think sometimes the textbook draws like a loop line over here. Yeah, it's kind of a, like for me, I'm fine if you don't put that on the exam, if you don't put an arrow there. Right. So, right. And then if we sometimes, right, I like to draw, right. So we're getting power from the first turbine, power from the second turbine. We're putting power in at the first pump. We put power in at the second pump. We add some heat here at the boiler, and we reject some heat at the condenser. Right, so this might be helpful if I'm doing something like trying to find my thermal efficiency, right, which we'll see later. It helps me sort of pick up which components I need there. So now the next part of the problem says, determine the heat addition in kilojoules per kilogram flowing through the steam generator, right? Or I wrote little q dot here, right? So here, this is going to be, sorry about that. This is going to be q dot of the boiler divided by m dot total, right? That's little q dot. Boiler or steam generator, I use those two words interchangeably. The textbook, when it says boiler, it means it only gets to a saturated vapor, and a steam generator goes further than that into the superheated vapor region. So now here, I would do the first law on the boiler by dt is equal to q dot plus, minus w dot plus the sum of m dot in, h in plus the kinetic energy term plus the potential energy term minus the sum of m dot out, h out plus the kinetic energy term out plus the potential energy term out. So the assumptions I'm going to make here for the steam generator or the boiler is that it's at steady state. This is a minus. You can disregard this thing over here. That it's passive, so there's no fan blades in there. That it's got one inlet and one outlet. And that we can neglect kinetic and potential energy. And if I do that, we get the Q dot of the boiler is going to be equal to M dot times H out minus H in, right? So H out is going to be here at state 1 and H in is here at state 7. So this is H1 minus H7. Now, the tricky thing is this is M dot of the boiler. And the thing that's tricky about Rankine cycles is that the mass flow rate through any individual component could be different than the mass flow rate through other components, right? So I could go back up here to this color-coded example that I have, right? And I see here that through this steam generator, I have the total mass flow rate, right? So now I can see that this is going to be equal to just M dot or M dot total maybe, H1 minus H7. And I can put that up into this equation and I'm going to get just H1 minus H7. Right, and this is good. We have an equation, right? I don't know any of these things yet. But I see that if I could fix the states, then I would be able to answer this part, right? Now, for the sake of this example, I want to go through all the symbolic stuff first, and then I'll show you how to fix the states at the end, right? So we will skip this now. And you could do this on a test too. Let's say you weren't comfortable with how to fix the particular states. If you still go through and you do the analysis and you get to these symbolic solutions, you're still demonstrating that you have some understanding of how to do these problems. Right? So I think that that's always a good strategy when you start with the equations and you make the assumptions, and then I can see what your understanding is, right? And future you, so if you were doing this at your work and then you came back to a problem like 4 years after you did it the first time, you know, it's like commenting code, right? Now you can understand what's going on. So now we're going to try to find the thermal efficiency. So with the thermal efficiency, we know that the definition here is it's the net work or the net power divided by the heat transfer rate in. So what I try to do is I try to identify what contributes to power, right? So here's the turbine 1, right? That's going to be a positive number from the first law. Here's turbine 2, right? Also a positive number. Here's pump 1. Oh, that's pump 2, sorry. And this over here is pump 1, right? And I coded those red because, you know, those are going to be negative numbers when we put them into the first law. And we already did the steam generator first law, so we've already done this, right? So now if I do the first law, dE by dt is equal to Q dot minus W dot plus the sum of M dot in, H in minus H out, minus the sum of M dot out, sorry, this is not right. Right, so this is H in plus V in squared over 2 plus GZ in, right, because it's a metric problem, plus V out squared over 2 plus GZ out. Right, now for the turbines and the pumps, I'm going to assume that we're at steady state. We weren't told anything about heat loss, so we're going to assume that that's small compared to the power. We're going to neglect changes in kinetic and potential energy. And each one of these components is one inlet and one outlet, right? The mass splits not inside any of the turbines, but at some node that's in between these two turbines. So these turbine and pump powers, they're still going to be the thing that we expect, m dot of the particular component times h in minus h out. And the turbine values will be positive and the pump powers will be negative. So here we're going to get, for the first turbine, I'm going to say m dot of T1, H1 minus H2, plus the second turbine, m dot T2, H2 minus H3. Now the pump powers, I'm still adding them, but they're negative numbers, right? So they're going to reduce my net power. This is going to be m dot P1, H4 minus H5, plus m dot P2, H6 minus H7. And this, I already did the boiler equation, right? This is going to be, we already know that this is m dot total through the whole boiler, right? And this is going to be h out minus h in, which is h1 minus h7. We've also already constructed this so that I know that through the second turbine, we get the whole, or the undiverted mass flow, just like we do through the first pump. And then the second pump gets the whole mass flow, as does the steam generator and the first turbine. So now here, I have to sub in. I can't just, if this was like a reheat cycle and we got to this point, we would just say all the mass flow rates are the same, so I'll cancel them out. But here we have this extra step, right? So this first turbine does get the whole mass flow rate. So that's going to be m dot times h1 minus h2. But the second turbine is going to get 1 minus y times m dot, h2 minus h3. The first pump also gets 1 minus y. This is now h4 minus h5. And the second pump does get all the mass flow rate times h6 minus h7. And that's the numerator. And my denominator is going to be m dot times h1 minus h7. Oops. There's an m dot in here as well. Right? Because remember, 1 minus y, that's just like a per unit or a percentage number if you multiply it by 100. So now everything is now multiplied by the total mass flow rate. And that's why we talk about it as like the percentage of the total mass flow rate, so that when we get to this equation, everything is still multiplied by m dot. So I can factor that out of the numerator and the denominator and cancel it out. And then I'm going to get that this thermal efficiency is just going to be h1 minus h2 plus 1 minus y, h2 minus h3 plus 1 minus y, h4 minus h5 plus h6 minus h7 divided by h1 minus h7. Now, if it was me, I would not go to the effort of memorizing this equation, because this equation is only going to be true if it's a open feed water heater that looks just like this picture. Instead, I'm going to trust the process, right? The process that I got here was I looked at where are the places that are contributing to the net power, do a first law everywhere there, and where are the places that are adding heat. And if you do that, it doesn't really matter how exotic the picture of the cycle that I give you is. You can go through and you can make the right equation for that case. Now, if the problem with this equation, right, is that even if I knew all these enthalpies, I still can't solve the problem because I don't know why either. So how do I find y? Oops. Now, y is a mass flow rate, right? Now, in this class, we basically have three strategies for finding a mass flow rate, right? So one, I know the area times the velocity divided by the specific volume. If I knew that, then I could find y. Number two, I look for some place where maybe they tell me the heat transfer rate or the power, and I do the first law. Right? So if in this case it told me that the net power was 1 megawatt, then I could use my net power equation, and if I could solve all the h's, then I could solve for y. Right? That's not the case in this case. So the other thing that we can do is we can do the first law on a component that's got more than one inlet and or more than one outlet. Right? So in this case, we don't know anything about the areas or velocities or anything anywhere. We're not told, how much heat is put in by the boiler, or how much heat is rejected by the condenser, or the net power or something. So instead, we have to do the first law on something that has more than one inlet and or more than one outlet. Now, I think no matter how we end up asking you a problem that's about regeneration, you're going to end up having to do a first law analysis on the feed heaters. So if you get to this point and you don't know what to do, or even if you're on one of these regeneration problems and you have no idea what to do, just write down the first law and do the first law on the feed water heater and or heaters, because it's going to be important, right? So now dE by dt is equal to Q dot minus W dot plus the sum of M dot in H in plus there's a kinetic energy term here and a potential energy term minus the sum of M dot out H out plus some kinetic energy and potential energy terms. So for the open feed water heater, it's steady state. It's definitely passive because it doesn't have any fan blades on the inside of it, right? It's not a turbine or a pump. No kinetic or potential energy changes. Now, this won't always be the case. You could have a feed water heater that is losing heat to the outside world. But in this case, and this is always a little bit tricky with these heat exchangers, we end up sometimes calling them adiabatic, right? That they're not losing heat. This doesn't mean that heat is not being transferred inside the control volume, right? These Q dot and W dot terms, they're about stuff that passes the border of our system. So in this case, it is adiabatic, right? And actually, in this case, if we look at the feed water heater, there's two inlets and there's only one outlet. So this open feed water heater, if we go back to this picture here, if I can, right? There's two inlets, state 2 and state 5, and there's one outlet. I can also look at this and I see that state 2 is coming in at y times m dot. State 5 is coming in at 1 minus y times m dot, and state 6 is going out at m dot. Again, that's why I like color coding it, because it makes it pretty easy for me to see just by looking at that picture. So now here, this is going to be 0 is equal to the sum of the mass flow rates in, right? So we said that y times m dot comes in at state 2, right? The other inlet was 1 minus y times m dot, and I think that was state 5. And then the outlet is the total mass flow rate times H6. So now, again, everything here, right? I can divide both sides of this equation by m dot. And then I can collect like terms, and I can see that 0 is equal to y times H2, right? So now I've taken care of this. And then this is minus y times H5. So this would be minus H5, right? So now I've taken care of this. And then it would be plus H5 minus H6. But the thing I want to do here is calculate y. So here I could say that y is equal to, I got to bring this stuff to the other side of the equation. So this is going to be H6 minus H5 divided by H2 minus H5. So now, right, if I call this, so if the equation for Q dot, my equation for little Q dot, if that was equation 1, my equation for thermal efficiency was equation 2, right, then this would be like equation 3, and I'm putting this into equation 2 to get an equation for thermal efficiency. This is, again, we're sort of in this place where I don't know any of these enthalpies, right? Now, this problem is asked in such a way that we don't know what Y is, but we do know what H6 is, or at least we could find H6. Some problems, maybe I'll tell you what Y is, but I won't tell you, like this problem, it told us state 6 was going to be at that intermediate pressure, but was going to be saturated liquid. I could not tell you what the quality is, but I could tell you the mass flow rate, right? I could tell you why. And then you would use this first law to find H6, right? So it's still going to be the same fundamental equations. It's just you're going to have a different thing that you're going to, need to look for. So now, after that, we will have been able to answer part C, at least if we could fix all the states, which we'll get to. Now we're asked to find how much heat gets lost by the condenser, right? So this is our control volume here. So again, right, when in doubt in thermo, write down the first law, right? Because the first law is kind of a big deal in thermodynamics class, right? Minus W dot plus the sum of M dot in, H in plus the kinetic energy plus the potential energy, minus the sum of M dot out, H out, plus kinetic energy plus potential energy. Now here for this condenser, because we don't know what's going on with the cooling water, we have to only look at the hot side of the condenser here. So here we'll say it's at steady state. It's passive. It's one inlet and one outlet on the hot side, right? And we will neglect kinetic and potential energies. So this is going to be very similar to the first part of the problem that we did, right? We'll find Q dot of the condenser is going to be equal to M dot times H out minus H in. So this is H4 minus H3. But remember, right, if I was drawing my mass flow rates here, right, this leg of the cycle gets 1 minus Y times M dot. So that's the mass flow rate going through the condenser side. So this is going to be 1 minus Y times M dot times H4 minus H3. Which means it doesn't want, the textbook is sometimes tricky this way. It won't say what's the heat transfer rate. It'll say like, what's the heat transfer rate per unit of, or per kilogram of steam flowing through the steam generator, right? So it's talking about M dot total, right? So we don't want to scale this just by the mass flow rate going through the condenser, because then it would have a different denominator than all the other things that we're scaling by the mass flow rate. So here my little Q dot C is big Q dot C divided by M dot total. And that's going to be 1 minus Y times H4 minus H3. So here again, right? Although at least we've got an expression for Y, but we don't have the number yet, right? I don't have H4 and I don't have H3. So even if I didn't know how to fix states, or if I was on an exam and felt like I didn't have enough time to fix the states, you could do this part, I think, more quickly, and it still demonstrates that you have some understanding about what's going on. Right? But now our job would be if I could fix states 1, 2, 3, 4, 5, 6, and 7, right? There's kind of a lot of them, right? Plus there's the, there's the 4 isentropic states that we have here too. Then I could find Y, and with Y, I can find the thermal efficiency and this little Q dot C. And then with the enthalpies, I can find little Q dot of the boiler. So now I won't get the numbers, but I'll walk you through the process for all of these, right? So here for state 1, this is nice because I'm going to assume that this is a superheated vapor, because if it's under the vapor dome, we can't fix this state because we need 2 independent intensive properties, and we have the pressure and the temperature. So here I'm going to assume that this is a superheated vapor, and I'm going to get this from table A4. I'm also going to pull off S from A4. Right? So now how do I do state 2S? So remember, this is an isentropic turbine, right? Or an ideal turbine too, right? So what I need here is I need to recognize that S of 2S is equal to S1, right? So this is going to be S1. Now I'm going to ask myself, is SF at P2S, is that going to be less than S2S, less than SG? So basically this is saying, is it going to be under the vapor dome, right? And if the answer to this is yes, then I'm going to find quality at state 2S, and I'm going to use that to find H of 2S. If not, then this will be a superheated vapor, and I will have to interpolate on table A4 to find A, or to find H2S. Right now, how do I then go through the real turbine, right? Because now I did the ideal turbine. How do I find state 2? Right now, I got to use the turbine efficiency. The turbine efficiency, right, is power over power. But the ideal turbine, remember, the turbine power is a benefit. So the ideal turbine gives us more benefit than the real turbine. So this is going to be m dot of turbine 1 times, this was H1 minus, it's H2 because it's the real turbine. M dot T1 still, H1, oops, H1 minus H2S. So in this problem, they told us the efficiency of the turbine. We already know H1 and H2S. So I use this equation to find state 2. Now, I just want to make sure we get to all the states. So I'm going to talk about state 3 pretty quickly, right? Because state 3, we do the same thing. First, we got to find state 3S. Remember, state 3 is coming out of, right? So now we found H2S and H2. State 3 is coming out of the second turbine, right? So now what we'd also have to do is when we found state 2, we would want to find S2 as well. Because state 3S is the same as S2. Right? And then I would have to figure out, is this going to be a 2-phase, or is it going to be superheated vapor, right? So if it's 2-phase, then I would have to interpolate to find quality, and then I'd use quality to find H2S or H3S. But in this case, or in this case, I don't know. But if it was superheated vapor, then I would have to use table A4, the superheated vapor tables. And then after I found, so this is the same, state 3S, I follow the same process. I'm going to have different numbers, but it's the same process. And then for state 3, I'm going to follow the same process, right? It's just now for state 3, this turbine efficiency is going to end up being H2 minus H3 divided by H2 minus H3S. right? And now the only thing that I don't know here is H3. So this is good. Now I know H3. H4 is kind of a gimme, right? Because here it tells me the pressure and it tells me the quality. So this is going to be HF at 6 kilopascals. This is going to be SF at that same pressure. And then here, you might not see this right away, and that's okay. But I'm also, if I'm going to look this up, I'm also going to look up VF at 6 kilopascals. Now, maybe some of you see why I did that, right? But so now we know state 4, and we're looking at state 5, but we don't do state 5 first. We do state 5S. State 5S is the outlet of the ideal pump. Now, as I go through ideal pumps, I know that H4 minus H5S, I have this, I'm going to assume an ideal pump, right? That's incompressible liquid on both sides. And that's going to be the specific volume, but I'm going to take the specific volume at 4 because it's incompressible. We're going to say they're about the same, times P4 minus P5. P5S and P5 are going to be the same thing. It only makes sense to talk about these pumps if they have the same pressure difference. Now, the only thing that I don't know in this expression is H5S. So I can use this equation to find the ideal outlet of the pump. Next, I do the real pump. This is state 5, right? And now I have the isentropic efficiency of the pump, which again is going to be power over power. But remember here, the pump cost, the pump power is a cost to the system, right? So the ideal pump power is going to be less than the real pump power. So this is going to be m dot through the first pump multiplied by the ideal on the top, so H4 minus H5S. Or if you like, remember, you probably don't ever have to find H5S on your table. So you could actually just take this part and put it in over here and never find H5S unless the problem specifically asks you for H5S. And this would be m dot P1 H4 minus H5. And the only thing I don't know in this expression is H5. So now when we go up here, we're going to be close on time. We know now H5S and H5. H6, this is another one, right? This is just like H4, except now the pressure is different. So this is going to be HF pressure is equal to 700 kilopascals, SF, and we'll also pick up VF at this intermediate pressure. And then I can do the same thing as I did here, where, so now this would be state 6S is going to be the same process as this, just the numbers are going to change, right? So that H5 minus H6S is going to be V5. No, this is 7S. So it's H6 minus H7S is going to be V6 times P6 minus P7 or P7S. It's the same thing. And then down here for state 7 is going to be the same as this, where my pump efficiency is going to be H6 minus H7S divided by H6 minus H7. And the only thing that I don't know there is H7. So, I mean, obviously it's going to take you more than the 10 minutes that we've spent doing this to fix all those states if you get numerical answers. right? But now we know all of these things. So because now I know all of these enthalpies, I can go back, right? And now I know, right? I can get numerical answers for all of these other things because I can find Y, right? And I know H4. And so now I know this heat transfer that we lose from the condenser. I can find my thermal efficiency, which is also, it doesn't really like scrolling with the numbers here. And then I can also find the heat that goes in. So that is, in a nutshell, how you do these Rankine regeneration problems. But again, if we take a step back, this process, if we use it for all of the cycles that we do, then you'll be able to see that it's really going to be the same thing that we do for every cycle. It's just, you know, maybe we use a different version of the first law if we say that they're closed systems, or maybe we find H in different ways because it's an ideal gas, but it's ultimately kind of the same thing. I'll take questions. I got a couple minutes still. Yeah. So the question is, in this open feed water heater, what we do is, because we bled that mass out, we took some of the mass flow between the two turbines. So that's still hotter than what it's going to be, or it has more enthalpy than what would come out of this pump. So when we mix those two things together at that same pressure, that's why we put that first pump there, then what happens is we get something out at state 6 that's got more enthalpy than when it went in at state 5. So this is kind of like we're preheating it before it goes into the boiler. What would be the what? Sorry? The closed feed water heater, the streams don't actually mix. So if you look at the picture for the closed feed water heater, this is maybe some kind of shell and tube. So the cold side of the mass flow rate would be like between a bunch of tubes. And then the hot flow would just go over that bank of tubes so that they would be able to transfer heat between each other. But the fluid from the hot side doesn't actually get to mix with the fluid from the cold side. Yeah, it's a good question. So what's the advantages and disadvantages? So this is tricky because I don't actually work in power, generation. So I don't know why they do one versus the other, but it's a good question. I think in real life, they'll do both. So like a real power plant is not just going to use, it's not just going to use reheat. It's not just going to use open feed water heaters for regeneration, or it's going to do all of these things together. And I'm sure, the engineers that are doing that, there are certain reasons why you pick an open feed water heater versus a closed feed water heater, but I don't know what those reasons are. You know. All right. I don't see any questions in the chat, so I hope everybody has a great day. I will see you Wednesday, either on Zoom or in person. Thanks, everyone. And I'll try to see what I can do about posting that video. So we'll see. I've never done that before, so we'll see.